Good day, grade 11s. Today we are going to go through a provincial examination, November 2025 paper. It's paper 2, chemistry. So just to go through it there, I'm going to scroll through the first page, which is our instructions and all, then proceed to the multiple choice questions, right? So now we're having our multiple choice questions there. Question number 1.1 reads the electron configuration there of an element is, so we're given an SP notation of this configuration, and then we're asked in terms of the valency of this element. So we need to know how many electrons are there. So according to this here, if we are to add all these 2 plus 4 plus 2, we're going to get a total of 8, right? So it means now we're having 8 electrons, right? So remember the electronic configuration, how we configure this one. The first shell is going to be complete with 2 electrons. Then after that, now the others are going to complete the next shell, which is our second energy level. So we're having, if we're to add there, it's going to be 1, 2, 3, 4, 5, 6, 7, and then the last one is 8 there. So in terms of our valence there, how many of these need to fulfill this shell there? So it means here, this one, if it's to accept electrons, it's going to accept how many electrons? 2 electrons. Therefore, our correct option is going to be option B, that says 2 there. Then after that, now we proceed to 1.2, which reads, the intermolecular forces holding the molecules in ice together are. So we're looking at the type of force that is holding the ice together, right? So in terms of the ice, just know this one is the same as your water. So it's just a change of state to formulate ice. So it's still our water. So in terms of this now, what we know in terms of our water, we have got our hydrogen bonds. So where do we find hydrogen bonds? So we need to know that whenever we're having hydrogen bonds is when our hydrogen is bonded to fluorine, oxygen, and also nitrogen. So in terms of this, our correct answer should be hydrogen bond. So our option D is going to be our correct answer. Moving on to question 1.3 reads, which of the following variables could be used to determine the temperature of a gas in a closed container? So which of the following variables can be used to determine the temperature of a container in a closed container, right? So in terms of temperature, we need to know the definition of temperature, which is defined as the average kinetic energy of the particles. So it means if we're having more energy, it means the temperature is going to be high. So the higher the temperature, the more energy these particles are going to have. So let's go through our options. The first option is the volume of a gas. This is incorrect, right? So as according to our definition of temperature. Then B is the average kinetic energy of the gas molecules. So our option B is going to be the correct answer. Then C, it talks about pressure, and then D, the mass of the gas. So all these are incorrect. So this one, we derive it from the definition of temperature. Then moving on to 1.4, 1.4 reads, which of the following represents 1 mole of the number 1 mole. So the number of what? So we need to know which of the following represents 1 mole, right? So mole is an amount of substance, right? So this is what we're having. Then our option A says the atoms in 6.02 times 10 to power 23 grams of sodium there. So our option A is incorrect. Our option A is going to be incorrect there because we're talking about the atoms in what? In grams of what? Of sodium. So A is incorrect. Moving on to the second option, which is B. So it says here molecules in 22.4 tm cubed of water at STP. Again, this one is going to be incorrect. Then they're saying protons in 1 grams of hydrogen gas. So our option C there is going to be the correct one. Then D says here molecules in 34 grams of ammonium gas. Also, this one is incorrect. Then 1.5 there reads the enthalpy in kilojoules per mole for the reverse reaction of the reaction below is, so we're given a reaction there. So by looking at this one here, we're given a negative, right? So a delta H is negative. Therefore, we know this is an exothermic reaction. So this is an exothermic reaction because our delta H is negative, right? So if you're asked why it's an exothermic reaction, it is allowed to use the symbol delta H is less than 0 as your reason. So this is a valid reason. So now they're asking us the reverse reaction of this, right? So it means the reverse reaction is going to be the opposite of this one. So instead of having an exothermic, we're supposed to have an endothermic, right? So it means our charge there, our energy should be positive. So here we're having a negative 120. It means the reverse is going to give us a positive 120 kilojoules per mole. So our option D is the correct one. Then moving on to 1.6, there is the process in which acids H plus and bases or H negative react to form a salt and water is called, right? So take note of one thing. if we're having something like this, there is a neutralization reaction. Do not like confuse these two with neutralization reaction, right? So where we are having an acid and a base, then in terms of this, they're saying the process in which acids, which is the proton, the H plus, and the hydroxide, which is your OH negative, react to form a salt and water is called, right? So option A says redox reaction. This is incorrect. And also B says displacement is incorrect. Then we also have our option D, which reads hydrolysis, also incorrect. So this is a synthesis reaction. So our option C is going to be the correct answer. Then moving on to question 2.1. 2.1 reads the draw a Lewis diagram of methane, right? So methane, we need to know that consists of a carbon and 4 hydrogens, right? So it's CH4. So our methane is CH4. So having our CH4 now, we're asked to draw a Lewis diagram. So if you can look at the configuration of carbon, you'll find that carbon has got how many electrons? 4 electrons on its outer shell there. So 4 electrons of around the carbon atom. And then remember, for it to be complete, then now we have our hydrogen. So how many hydrogens are we having there? According to our formula, we're having 4 of them. So it means I'm going to add an H there, an H there at the top again, like that, and then an H again here, and also an H way at the bottom. This is the Lewis diagram of methane derived from CH4. Then moving on to 2.2 reads there, what is the name of the special kind of bond found inside the methane molecule, right? So inside the molecule here, methane, our CH4, we have what we refer to as a covalent bond, right? Covalent bond. So our answer is going to be covalent bond, right? So remember, if we're saying covalent bonding, they were talking about the valent electrons, the electrons that are found on the outer shell, that are the ones that are used for bonding. Then 2.3 is there. Answer the following questions about magnesium chloride. So this is our MgCl. Then they're saying make use of Lewis diagrams to indicate the transfer of electrons between magnesium and chloride. So there is a transfer of electrons. So in terms of our Mg, we know Mg is in group 2. So it means it's going to have how many electrons on the outer shell? 2 electrons then. Then after that, if it's to transfer electrons, this is what is going to happen to Mg. So our Mg is going to formulate something like Mg, then Mg, then 2 plus, right? So the positive charge there shows that it has given what? Electrons. So if it gives out electrons, it will remain positive because now it's having more protons than electrons. Then we're going to say plus 2e to show that these are the electrons that were given out. Then after that, we also need to indicate the 1 for chlorine. So for chlorine is going to be 2. Then I'm going to put our chlorine. So chlorine is in group number 7. And because it's in group number 7, it means it has got 7 electrons on its outer shell. So it's 1, 2, 3, 4. Remember, you start by circling the 4. Then after that, you add the right. So it's going to be 5, 6, 7, right? So this is what we're having then. Then I'm going to add your 2 electrons there plus 2 electrons, right? So we're going to get a configuration that looks like this for chlorine. Therefore, it's going to be 2 there. Then brackets, I'm going to put a Cl. Then now I'm going to indicate the electrons that we are having there. 1, 2, 3, 4, 5, 6, and 7, 8, right? Then I'm going to put a negative. So that negative there represents or shows that this chlorine has gained an electron. Then the 2 there represents that we are going to have how many electrons? 2 chlorines. We're going to have 2 chlorines. Then moving on to 2.3.2. Raise here, magnesium chloride is an ionic substance. So we're told this is an ionic substance. Prove the statement with an appropriate calculations, right? So in terms of this, we are supposed to look at the electronegativity values of chlorine, right? So if we're going to say En for chlorine, En then Cl, then let's go to our data sheet to see what's the electronegativity value for chlorine. So I'm going to quickly scroll down to our data sheet so as to see the electronegativity of chlorine. So the electronegativity for chlorine, we find it on our periodic table, right? So let's look at the electronegativity values of chlorine. So Cl there, we're having an electronegativity of 3.0, right? So how did I find this one? Here, as an example, we are given there the electronegativity value for what for copper. You can see it's represented there as being 1.9. So you can see as we are moving to the right, what happens to your electronegativity values? It actually increases. But as you are going down the group, it decreases. So electronegativity increases from as we are going moving from left to right, and then it also decreases down the group. Then that's the E theta, or the electronegativity value for chlorine, which is 3.0. Then we're going to scroll back to our question. Electronegativity value for chlorine is 3.0. Then also what do we need? We also need the one for magnesium. So En for Mg, the En for Mg is equivalent to, so I'm going to have an El value for Mg. I'm going to get a value of what? Let's go back again and look at the E theta value for magnesium. I'm going to have a value of 1,2. So that's the value for magnesium there, 1,2. Then scrolling back there, I'm going to say En value for magnesium is 1,2, right? So for us to find the change in En, it's going to be delta En there, which is our electronegativity value, is equivalent to the one for chlorine is 3.0, and then the one for magnesium is 1,2. Then if I subtract there, I'm going to get a value of what? 1,8. So if I'm getting a value of 1,8, it means my substance is ionic. So that's how we conclude our 2.3.2. Then moving on to question 3. Question 3 reads there. In the table below, the boiling points of 4 hydrogen halides are given, right? So we're given the boiling points of 4 hydrogen halides, right? So these are the boiling points of 4 hydrogen halides, right? Are given below. Then they're saying define the term of boiling point. So these are the table there that we're having the boiling points in hydrogen halides, HF, HCl, HBr, as well as HI. So the first thing they were supposed to do is to define the boiling point. So boiling point is defined as the temperature at which, so the temperature, so if you look at your exam guide, you will find that the temperature is going to be always underlined, right? So I'm going to say the temperature at which the vapor pressure, equals atmospheric pressure, equals atmospheric pressure. So this is how we define our boiling point. Please make sure to use your exam guide when it comes to definition of terms, right? Then 3.2 says here, what is the relationship between the strength of the intermolecular forces and boiling point, right? So let's look at the intermolecular forces and the temperature, right? So if we can look, the relationship between intermolecular forces is that whenever you are having a stronger intermolecular force, you are also going to have a higher boiling point. But take note, do not use the relationship that says HF, the intermolecular forces, is directly proportional to the strength of the forces, right? We are not supposed to use that one. So we're going to say the stronger the intermolecular force, the stronger I'm going to write IMF, right? IMF, which is for intermolecular forces. But please take note, we are supposed to write this one in what? In full, right? The stronger the intermolecular force, the higher the boiling point. The higher the boiling point. So I'm going to just write BP there, which is for boiling point. Then I'm going to proceed to question 3. So question 3 is there. Which of the hydrogen halides A, B, C, or D in the table below above has the highest vapor pressure, right? So in terms of this, the one that is going to have the highest vapor pressure is going to be B, right? So our answer there is going to be B, which therefore is referred to as our HCl, right? So in terms of explanation there, if we're having a higher boiling point, right? So a higher boiling point there, we're going to have a lower vapor pressure, right? So it's more of like saying BP, which is our boiling point, versus our vapor pressure, right? So I'm saying if we're having a high boiling point this side, the vapor pressure is going to be low, right? Again here, in terms of BP, if our boiling point is low, our vapor pressure is going to be high. So in terms of this, the highest vapor pressure, it means it's going to have what? The lowest boiling point. So according to our values there, you can see the negative 85 is the lowest value there. So that's what we're having is this one, right? So the relationship there is inversely proportional, right? So it's going to be our lowest there. And then giving a relationship, say lowest boiling point, I'm going to write BP there. So we know vapor pressure is inversely proportional. Vapor pressure is inversely proportional. So inversely proportional to boiling point. I'll just write BP there. Then moving on to 3.3.2, it says the strongest intermolecular forces. So which of these has got the strongest intermolecular forces, right? So the strongest intermolecular forces is the one that is going to have the highest boiling point. So according to this, 19 is the highest boiling point. So our answer there is going to be for 3.3.2 is going to be A, which is your hydrogen fluoride there. So it's A or HF. Then moving on to 3.4, it says draw a line graph to represent the boiling points of these hydrogen highlights. Then clearly label the axes and give the graph a heading, right? So there I'm going to draw something here. I don't know if I was provided with a graph paper. So I'm going to proceed to the next one and try and draw it here, right? So I'm going to have different values. I'm going to have different values in terms of this. I'm going to have different values. Okay, so now we've been asked to draw a line graph. So it says draw a line graph there to represent the boiling points of the hydrogen halides, right? Then we're supposed to label our axes clearly and give the graph a heading, right? So now going to say the boiling points. So I'm going to say our heading there, boiling points of hydrogen halides, right? Of hydrogen halides. Right, so in terms of our graph, it's going to appear like this, right? So I'm going to formulate an x-axis. Then on this other end, what I'm going to have here, I'm going to say, let's have our boiling point to the right, our boiling point. Okay, so then from our graph there, we're supposed to plot these values that we are having there. Then according to this, our analysis shows that the maximum value that we are having there is 19, which is more positive, and then the others, the most negative is going to be 85, right? So according to this, I can use a scale of 0, maybe going upwards as being positive there, then going downwards as being what positive, from the origin going downwards as being a negative. Then I'm going to say my scale here is going to be a positive. The maximum value that I'm having there is a positive 20. Therefore, I'm going to say plus 20. Then going down there, I'm going to say a negative 20, negative 60, and then negative 80. Then these are the values that we're having. Then according to this, then I'm going to plot these values. So here we're having HF with a value of 19.4. It means it's towards 19.4. Then that's our HF there. So I'm going to have around 20 there. I'm going to start with my HF there. Then after that, the next value that I'm having is going to be a negative 85. Then there is also a negative 35, so it's a negative 85. Therefore it's almost here, so it's a negative 85, so I'm going to put it somewhere there. So according to this, our 85 there is HCl, so I'm going to have our HCl there at the bottom. So then after that, the next one according to the table there is 67, which is our HBr. So I'm going to say around here I'm having a value of 60, therefore I'm going to put a 67 there, which is our HBr. And then finally we also have our HI, which is our hydrogen iodide there, which is negative 35. So it's going to be in between 60 and that one. Therefore, I'm going to have my HI. Then after that, I'm supposed to join all these points there. So I'm going to use a black color there to join all these points. So we are going to have a graph that looks like that there. So this is how it's supposed to appear. Then I'm going to proceed to 3.5 that says compare the compounds there. Compare the compounds A and B, and refer to the intermolecular, the type and strength of the intermolecular forces and energy needed to explain the difference in boiling points between hydrogen halides, right? So this is what we are having according to the question. Then I'll proceed and say here, in terms of the comparison there, I'm going to compare the hydrogen halides. So the first one that I'm going to like mention there is going to be our hydrogen halide, right? So it's hydrogen halide there. So which is our A, or I can just say A there, right? Or HF, right? So HF there at the top, the one that is the highest boiling point, which is our hydrogen halide A there. So I'm going to say according to this, have hydrogen bonds. So I'm going to say this one has got hydrogen bonds, right? So HF has hydrogen bonds. I'm going to say he has got hydrogen bonds, right? Then after that, now, after having hydrogen bonds, we're going to proceed and say The others, what do they have there? I'm going to have like A and B. So they're saying A and B. So B is HCl. According to that HCl there, what do we have there? They're saying compare compounds A and B and then refer to the type of intermolecular forces. Therefore, it means our B there, I'm going to say what do we have there in terms of our B? This is our HCl there, right? So compare the compounds A and B and refer to the type of intermolecular forces. Then in terms of our D there, what are we going to have there? So if you look at D there, at B there, sorry, instead of D is supposed to be B. If we were to look at B there, what do we have there? We're having the most negative value, right? So in terms of this, the negative value there, what do we have there? It's an HCl, right? So no more HCl is more, we can say it has got what? A dipole, right? So I'm going to say this one, dipole, right? So I can say dipole, right? So in terms of the strength, hydrogen bonds are stronger than this dipole, right? So I'm going to say more energy is needed, more energy is needed, more energy is needed to overcome intermolecular forces, to needed to overcome. I'm going to write IMF for intermolecular forces, right? In A than in D, in A than in D, right? In D. So it means here we need more intermolecular. The stronger the intermolecular forces, the more the energy is needed, right? To overcome intermolecular forces in what? In A than in D. This is because we deduced in terms of the boiling points. A has got a higher boiling point, while D has got a lower boiling point. Then moving on to question number 4. Question number 4 reads here. So question 4 reads, the diagram below shows a sketch graph of the product PV against P for 1 mole of oxygen gas at 0 degrees, the solid line, right? Then after that, the dashed line represents the relationship of 1 mole and an ideal gas at 0 degrees. Then the first statement then is asking us to define, right? So definition of terms there, refer to exam guide. It says here, define what is meant by the term ideal gas, right? So it's is a hypothetical. So this one, it is a hypothetical, hypothetical, okay, hypothetical guess that will obey all gas laws, right? Obey all gas laws under all conditions of temperature, under all conditions of temperature. Allow me to use degrees Celsius and pressure, right? And pressure, like that. Okay, so that's how we define our ideal gas. Then they're saying exactly 3 moles of a gaseous compound occupies a volume of this at 15,8 degrees Celsius. Then calculate the pressure of the gas at this temperature in kilopascals, right? So now, according to this, we're going to use or manipulate the formula that says PV is equivalent to nRT, right? So PV is equivalent to nRT, right? So where your P is the pressure, then I'm going to say P. Then in terms of the volume there, let's look at the volume. How much volume are we given in terms of this, right? So I'm going to say the volume there that is given, it says there, according to this there, what do you have there? Dash line represents the volume relationship of 1 mole of a gas at that temperature. Then what do we have there? We're having this volume in dm cubed, right? So it says calculate the pressure of the gas in what? In kilopascals, right? So that's the volume that we're having. Then I'm going to convert that volume to cubic centimeters, right? So if we were to convert it, what are we going to get there? We're going to get a volume of what? 0,012. 0,012 is equivalent to then the n there. So the n refers to this number of what? Of moles, right? So we're having 3 moles there, right? So I'm going to say 3 multiplied by 3. Then the R is our gas constant, right? So it's there on our data sheet, which is a value of what? 8,31. Just to show you there at the bottom where we find our gas constant, this is the gas constant R, right? So it's going to be 8,31. So I'm going to say multiplied by 8,31 there. So to proceed there, multiplied by 8,31. So it's going to be 8.31. Then multiplied by the temperature, right? So now what do we have there? So we should take note there. We're having 15 degrees, 15,8 degrees, right? So I'm going to say 15,8 degrees, 15,8 degrees. Then add there. So I'm going to add the Kelvin temperature, which is our 0 degrees, which is 273, right? So if we were to do our math there, P is equivalent to, so according to my math there, if I do the calculations, I'm getting a value of what? So it's a matter of us making P the subject of the formula. We're going to get a value of 599 and then 982 pascals, right? So now, as a conversion there for our kilopascals, so it means P is equivalent to a value of 599, 9898. I can now say kilo or pascal. So that's how we go about that one. Then after that, now they're asking us 4.3, which says if the volume of the container in the reaction in question 4.2 is doubled, what will happen, right? What will happen to the pressure of the gas, right? So we're focusing on the pressure of the gas. If this one is actually what? Doubled, right? So write only increase, decrease, or remain the same, then explain your answer. So our correct answer there is going to be decrease. So we're going to say decrease. Then our answer there is going to be decrease. I'm going to say decrease. Then now we need to put a reasoning behind, right? So now the pressure of a gas is inversely proportional. So I'm going to say the pressure of the gas, the pressure of the gas is inversely proportional. So it's inversely proportional to the volume to the volume of a gas at a specific temperature, temperature. Okay, that's how we answer that one then. Now moving on to question number 5. So question number 5 there reads, a brisk effervescence is seen when diluted hydrochloric acid reacts with what? Sodium carbonate, right? So there's a reaction between HCl and sodium what? Carbonate there. Then we're given the balanced equation for the reaction as follows, right? So now it's sodium carbonate plus HCl there, hydrochloric acid, to give us sodium chloride plus carbon dioxide and water there. So that's our equation then. Then they're asking us to write down the formula of the substance that causes the brisk effervescence that is seen there, right? So there, the brief effervescence that is seen there is caused by the gas, right? So it's going to be your carbon dioxide. So the answer there is going to be your CO2, right? CO2, which is your carbon dioxide gas, right? Then 5.2 says in a reaction 10.6 grams of sodium carbonate. So we're having the number of the mass there that is given is 10.6 grams of what? Of sodium carbonate reacts completely with excess hydrochloric acid. So we know our HCl is in excess. Then we were asked to define 1 mole of a substance, right? So to define this one here is defined as the amount of substance. Remember, the mole is the amount of substance, right? So this is the amount of substance, okay, having the same amount of substance, that is having the same number of particles, as there are atoms in 12 grams carbon 12, right? So C12 there. So that's how we define our mole of a substance, right? Then there's asking us 5.2 there, which substance is the limiting reagent, right? Give a reason for your answer, right? So I'm going to say sodium carbonate is our limiting reagent, right? So the Na2CO3. Okay, so the question might arise, where do I get this one, right? So here we're given there, it says here reacts with sodium carbonate. The balance equation is like that, right? So we are also told under 5.2 there, it says reacts completely with excess hydrochloric acid. So we're told already hydrochloric acid is what is in excess, right? So what does that make a sodium carbonate be? It makes it a limiting reagent. So it means it's going to be used up. So it's going to determine the amount of product that is going to be formulated, right? So because now the reason behind there, I can say because it reacts with excess excess HCl. So we're told there at the top that HCl is in excess, right? Then 5.2.3 is there. Calculate the mass of carbon dioxide produced during this reaction, right? So we're looking for the mass of what? Of carbon dioxide there that is going to be produced during this what? Reaction, right? So for this one there, we are supposed to say 5 point what? 5 point, okay, 5.2.3 there. We're asked to calculate the mass of carbon dioxide there. So I'm going to proceed and say, in terms of this, what you are going to do there is to calculate the mass there, right? So let's start with the data that we are having, right? So let's calculate the molar mass of what? Of sodium carbonate, right? So it's going to be Na2CO3 is equivalent to, so according to this, we know the mass for sodium there is going to be 23, right? So I'm going to say 23. Then according to this, we're having two sodiums. Then I'm going to say plus. Then our carbon dioxide there is carbon 12. Then multiplied by only one carbon. I'm going to proceed and say plus. Then our oxygen there, we have got 16. And then we've got having three oxygens, right? So if we were to do our math there, we're going to get a value of what? If I add 23 times 2, then plus 12 times 1 plus 16 times 3, I'm getting a value of 106, right? So remember, this is the molar mass, so it's going to be in grams per mole, relative molecular mass of this there, right? It's going to be in grams per mole. Then proceeding to the next part there, now we're supposed to calculate the number of moles, right? So the number of moles of what? Of sodium carbonate, right? So in terms of this, the formula for sodium carbonate is equivalent to the number of moles there is m all over m, the mass all over the molar mass, right? So if we were to proceed there, is equivalent to, so according to this, what are we given? We're given the mass of this sodium carbonate, right? So is 10,6, right? So it's going to be 10,6 there. This is the given mass. So I'm going to say 10,6 all over the whole molar mass, right, which is 106, right? So if we were to do our math there, we're going to get a 10,6 divided by 106. I'm getting a value of 0,1. I'm going to say 0,1 moles, right? So going back again, so that we put a reminder there, we are looking for the mass of what? Carbon dioxide that is going to be what? To be produced there, right? So in terms of this, now we have got our mole ratio, right? So we're going to focus on the mole ratio. According to this, is going to be 1:1, right? So I'm going to say, to proceed and say mole ratio. So the mole ratio between what and what? Between sodium carbonate, right? So Na2CO3 versus our carbon dioxide, which is our CO2, right? So the mole ratio there is 1:1, right? So if it's 1:1, it means we're going to use the same number of moles for what? For carbon dioxide. Therefore, if I'm using 0,1 this side, so also this side I'm going to use the same number of what? Of moles, which is 0,1, right? Then after that, now I can proceed and calculate what? The mass of this what? Carbon dioxide, right? So in terms of this, I'm going to say the number of moles of CO2, remember, is equivalent to m all over m, right? So to proceed there, I'm going to say the number of moles we already have is 0,1 is equivalent to the mass that is given there. This is what we're looking for, all over the molar mass of carbon dioxide. Remember, carbon is 12, right? So I'm going to say 12 times 1, and then I'm going to say plus, then our oxygen is 16, then times 2, right? So if we do the mass there, the molar mass, making it the subtractive formula, we cross multiply. So it's going to be 0,1 multiplied by 44. Therefore, we're going to get a value of what? 4,4 grams. So this is the mass of what? Of carbon dioxide that is going to what? To be produced there. So we're done with that question, which is our 2.3, if I'm not mistaken. Yes. Then proceeding to question 5.2.4 is the calculate the mass of what? So we're looking for the mass of sodium chloride, right? So as a product, so sodium chloride, if you can look there, is a product produced if 4,87 dm cubed of carbon dioxide is produced at what? Is STP, right? So to proceed in terms of this, now we're going to say the number of moles of carbon dioxide there, right? So in terms of this, we're going to say the number of moles of CO2 is equivalent to, so remember, we're looking for the volume, right? So it's going to be V all over Vm, right? So this is how we calculate this one. Then according to this, what are we given? We're given the volume of carbon dioxide there is 4,87 there, right? So it's 4,87 dm cubed. So there is no need for us to convert that one. Therefore, I'm going to say 4,87, right? All over the molar gas volume. So the molar gas volume is a constant, right? You find it on your data sheet there, which is 22,4. Therefore, I'm going to get a value of what? So it's 4,87 divided by 22,4. I'm going to get a value of what? 0,217. Then I'm going to say moles, right? So take note there. We're starting with this one so that we can use the mole relationship, right? So now we're looking for the mass of what? Of sodium chloride there. So before we can proceed now, we're going to use the mole ratio. So the ratio between our what? Our carbon dioxide and our sodium chloride, right? So CO2 versus our NaCl, right? So NaCl. So if we were to go back again here, we're going to say our sodium chloride here, you can see is 2. Then our carbon dioxide there is going to be what? To be 1, right? So it's going to be 2 is to 1. So it's 2 is 2 is to 1. That's the ratio there. So it means carbon dioxide there is got 1. Then this one is 2. So what does that mean? It means now if we're having 0,217 this side there, this side is going to be a double. So it's a matter of multiplying 2 multiplied by 0,217, right? So if you multiply there, we're going to get a value of what for sodium chloride? I'm getting a value of 0,435 moles, right? So these are the moles for what? For sodium chloride. Then after that now, we are going to proceed and say how to calculate the number of moles, right? So to be specific, we are calculating the number of moles is equivalent to the mass all over the molar mass, right? So already now we're having the number of moles there. So it's 0,435 is equivalent to, so take note what we asked to calculate there. They're saying the mass of what? Of sodium chloride. So we're looking for the mass of what? Sodium chloride. Again, that STP gave us this formula where we were dividing 22,4 because this is the molar gas volume at STP, right? So it means here I'm going to say the M that we're looking for all over the molar mass for what? For sodium chloride, right? So if we can look at sodium is 23, then multiplied by 1, then plus the chlorine is 35.5, 35,5, and also multiplied by 1, right? So we're going to cross multiply to make M the separate formula. So the mass of sodium chloride, the NaCl now is going to be, so if we cross multiply the 0,43.5, 0,435 multiplied by 58,5, I'm getting a value of 25,44 grams, right? So this is the mass that we've been looking for. So with that being said, we are done with that question. So proceeding to the other question there, which is our question 5.3, says here the empirical formula of a gas is NO2. Then 46 grams of this occupies 11.2 dm cubed at STP, again standard temperature and pressure, right? State Avogadro's laws that you will use with this information, right? So now let's state our Avogadro's law there. So I'm going to say 5.3.1, right? So this is our question. Then I'm going to say 1 mole of any gas, 1 mole of any gas, right? Of any gas occupies the same volume at the same temperature and pressure. At the same temperature and pressure. Okay, so that's how we attempt 5.3.1. Then moving on to 5.3.2, they says find the molecular formula of this compound, right? So now I'm going to make use of a statement for us to be able to explain this one, right? So 5.3.2, right? So it means here, if 46 grams, according to this, what do we have there? We're told 46 grams, right? So I'm going to say if of 46 grams occupies, we're told half there. Half of the molar gas volume of the molar gas volume there. Therefore, then the ratio is 2:1, right? So it's half. Therefore, it means it's 2:1, right? So now to conclude there, that's molecular. That's the molecular formula to be able to occupy 22,4 dm cubed STP is N2O4, right? So that's how we work out question 8.3.5.3.2 there, right? That's how we answer that question then. Moving on to question 6, right? So here they're saying start on a new page and all, right? So they're saying the diagram below represents the potential energy changes. So we're looking at the potential energy changes for an endothermic reaction, right? So the type of reaction that absorbs heat from the surroundings, right? Then after that, now we are asked to analyze, maybe just by analyzing. Then after that, now they're asking us what is going to happen, what is going to happen there, what will happen to the temperature of the surroundings, right? So what is going to happen to the temperature of the surroundings of the above reaction, right? So now what is going to happen in terms of this day is that the surroundings is going to be cooler, right? It's going to get cold. Why? Because this is an endothermic reaction and absorbs it from the surroundings, right? So around down surroundings there, I can say surroundings. What happens to the surroundings? Surroundings cool down, right? So because this is a reaction that absorbs it from the surroundings, right? Then proceeding to the next part there, it says which lettered interval or combination letters on the diagram represents activation energy for the reverse reaction, right? So we're looking at the reverse reaction, right? So the reverse reaction is going to be this one there that represents the reverse reaction, right? So it means now we're going to have N and E as our letter, right? So it's going to be E there. So our E represents the reverse reaction. Then proceeding to 6.3, it says if a catalyst could be used, right? So if a catalyst could be used to improve efficiency of this reaction, explain how a catalyst would affect the potential energy in this reaction, right? So it means a catalyst is a substance that speeds up the rate of reaction. So having said that, it means now what is going to happen there is that it will lower activation energy. So if a catalyst, it will lower activation energy, it will lower activation energy activation energy. So it will lower the activation energy by providing an alternative pathway, right? So pathway like that. So this is what we are having in terms of that there. So now to proceed to the next part there, what we are going to have. So now we're saying the next question says read through the graph in your answer book and indicate the changes of the reaction when using a catalyst using a dotted or a dashed line, right? So I'm not going to read through. What I'm going to do there is to make use of this graph that we already have here. So I'm going to just like use a dotted line, right? So look at so we're trying to lower the activation energy there. So this is the part that this one is going to have to follow like that, right? So that's how it's going to look like. Then to proceed to the next question, which is our question 6.4, they're saying using only letters from the graph above, derive a mathematical formula to calculate the change in enthalpy of this reaction, right? So the change of enthalpy in this reaction, right? So remember your enthalpy is going to be, I'm going to say delta H is equivalent to H products, right? Basically, this is what we're having minus H reactants, right? H reactants, right? Then it means here I can conclude and say our delta H is equivalent to. So now let's look at the energy of the products there, right? So our energy of the product there is going to be our D, right? Then the one for the reactants there is going to be what to be A there, right? So it's same as what products minus reactants. Therefore, I'm going to say D minus A there. So that's how we answer that one, because they said using letters from the graph above derive a mathematical formula. So this is the mathematical formula that they're looking for. Then now to proceed to the next question, which is question 7.1. They are saying here when sulfuric acid reacts with water, so it's sulfuric acid reacting with what? With water, it ionizes into two steps as shown in the two balanced equations below, right? So this is the first part and then this is the second part, right? So now they're saying give the Lowry-Bronsted definition of an acid, right? So an acid, according to this, it is a proton donor, right? So it is a proton or proton like that. Then I can just say maybe in brackets H plus donor, right? So it is a proton donor. So that's how we define a what? A Bronsted Lowry acid, right? So it is a proton donor. Then after this, they are asking us to write down the formula of the conjugate acid of what? H2SO4, and the conjugate base of what? HSO4, right? So now from our definition there, we know that our conjugate acid is going to be H2SO4, right? From the top there, right? So if you look at this equation, this one is going to be paired with what? With HS, and then this one is going to be paired with that. So now we know this one is going to be our acid, right? So this is the conjugate acid, right? Conjugate acid. Then after that, now the second part there, the conjugate base of this one is going to be SO. So they were having that one there, and then it will go with S, and then this one also still going to go with that one there, right? So the conjugate base of this one here is going to be, if I had to write down there, it's going to be SO4 2 negative, right? And then for that one there, the conjugate acid is going to be our H2SO4, like that, right? So these are our answers. Then proceeding then to the next part there, maybe I can also include state symbols there. So this is arc, and then arc, like that, right? Then to proceed there, question 7.1.3 says, which one of the compounds in reactions 1 or 2 is an ampholyte, right? So we need to know what an ampholyte is, right? So an ampholyte is a substance that can either act as an acid on or a base, depending on the type of what of reaction, right? So in terms of this here, we have got our water, right? So I'm going to say our ampholyte there is going to be our H2O, right? So I'm going to stick with water, which is our H2O, right? So which one of the compounds in reaction 1 and 2? Oh, so reaction 1, there, the ampholyte is going to be our HSO4, right? So this one can either act as an acid or a base, depending on the type of what of reaction. So I'm supposed to start with it there. I'm going to say HSO4 with a negative, right? And then for the second one there, we're going to have our H2O, which is this water there. So it's going to be this one. It acts as what? As an acid, and then on the other part is acting as what? As a base, right? So that's what we're having. Then to proceed to the next part, which is 7.2. So 7.2 reads the inner titration. The learner finds 20 cubic centimeters of 0.2 mole per dm cubed solution of hydrogen carbonate, and neutralizes 12 cubic centimeters of the sulfuric acid solution. Then the balanced equation for this reaction is, so we're given a balanced equation, right? So now in terms of this, why is H2SO4 regarded as a strong acid, right? So here, in terms of your reasoning, we are supposed to define a strong acid, right? So an acid ionizes completely. So basically, I'm going to define what a strong acid is. So an acid ionizes completely, right? Completely. Okay. So completely in water, in water. Okay. This is in water, to form a high concentration, a high concentration of H3O plus ions, right? So if it was a weak acid, it was going to ionize partially or incompletely to form a low concentration of what? H3O plus ions, right? So here, basically, they were asking us to define a strong acid, right? Then 7.2.2 says how many moles of sodium carbonate, right? So how many moles of NaHCO3 are present in 20 cubic centimeters of that, right? So now we're looking for the number of moles there, right? So in terms of this, I'm going to manipulate this formula that says the number of moles of B, right? So number of moles of B is equivalent to CB. I can also say VB, right? So concentration, remember, concentration is equivalent to number of moles all over the volume. So it's a matter of me making the number of moles the separate formula, then to multiply concentration and what? And the volume, right? So in terms of this there, let's look at the concentration there. We're given a volume of what? A concentration of 0.2 dm cubed, right? So I'm going to say 0.2, therefore I'm going to say 0.2, then multiply with the volume, right? So look at the volume that you're given there. You're given a volume of what? 20 cubic centimeters, right? So this 20 cubic centimeters, we're supposed to convert it to dm cubed by multiplying it by 1,000, right? So I can just say 20 multiplied by 10, dividing it by 1,000, 10 negative 3, like that, right? So it means now if I do the math there, 0.2 multiplied by 20 times 10 exponent negative 3. I'm getting a value of 4 times 10 negative 3 moles, right? So these are the number of moles, right? So that's our answer then proceeding to the next question. The next question there is 7.2.3, right? So we're asked there to determine, it said determine the number of moles, right? So we're looking for the number of moles specifically of H2SO4 that are neutralized, right, by 20 cubic centimeters of 0.2 moles of what? Sodium hydrogen carbonate, right? So now to conclude that one there, we are going to use the number of moles, right? So in terms of this mole ratio there, we can see the mole ratio there is half the volume of the what of the base, right? So this is one, this is two, then this other one is one, right? So the ratio there you can see, you can say is two one, right? So having that relationship there in mind, then we're going to say the number of moles there. Specifically, I'm going to say A regarding what an acid, right? So it's going to be the half the number of moles of the what of the base there, right? So what did we have there? So it means the number of moles of the acid there is going to be what? Half multiplied by the number of moles of the base that we calculated. There we calculated and got a value of what? 4 times 10 negative 3, right? So multiplied by 4 times 10 negative 3, right? So if we were to do the math there, we're going to say half of 4 times 10 negative 3. I'm going to get a value of what? Of 2 times 10 negative 3. Therefore, I'm going to say my answer is now in what? In moles, like that, right? So that is our final answer. Then to proceed to the question 7.4 says calculate the concentration, right, of H2SO4 in solution, right? So by formula, you know your concentration there. Your concentration is equivalent to a number of moles all over the volume, right? So maybe let me just say 7.2.3. Then now we're on 7.2.4, right? So concentration is equivalent to the number of moles all over the volume, right? So this is equivalent to, so if we were to proceed there, we're going to get a value of what? The number of moles we already calculated there is 2 times 10 negative 3. So it's a built up on this question that we're having 7.2.3. Then after that, now we need to look at the volume, right? So the volume that is given there, what are we given there? At the top, we're told of 12 cubic centimeters of what? Of sulfuric acid, which is your H2SO4. Then I'll proceed to say here, to convert there, I'm going to say 12 times 10 negative 3, right? So it's a matter of like for you to convert cubic centimeters to dm cubed, you divide by 1,000, right? So if you divide by 1,000, you're still going to get the what? The same value. So if I say 2 times 10 negative 3 all over 12 times 10 negative 3, I'm getting an answer of 0.17. Then this one, remember, is concentration. Therefore, the units of measurement should be mole per dm cube. Then proceeding to question number 8. So question 8 there is the question 8 says the lab assistant stored zinc sulfate. So we're having zinc sulfate, which is ZnSO4, in an aluminum, right, Al container. Then after a while, the teacher noticed that the aluminum container is eroding, right? So, and she suspects a redox reaction, right? So there is reduction and oxidation, right? So the teacher writes down the following unbalanced reaction, right? So define the redox reaction, right? So what's a redox reaction, right? So a reaction that involves electron transfer, right? So a reaction that involves a transfer of electrons, a transfer of electrons, right? So this is how we define our redox reaction, right? Then after that, they're saying calculate the oxidation half reaction for this reaction, right? So in terms of that, the oxidation half reaction, right? So now we should be able to identify which one undergoes oxidation, right? So oxidation is the loss of what? Of electrons, and then reduction is the gain of electrons, right? So in terms of this one, the aluminum is the one that is losing electrons in terms of this. So I'm going to say my Al there, arrow, then now if you can look there, it's supposed to be Al3 plus, right? So I'm going to say Al is going to be Al 3 plus, then plus how many electrons? So plus 3 electrons, right? So oxidation is the loss of electrons. So we can see from that equation then here reduction, right? half cell, right? Reduction is defined as the gain of what? Of electrons, right? So which one is gaining electrons there? We will take note that is zinc that is gaining what? Electrons there, right? So I'm going to write the equation as Zn 2 plus, so it's going to be Zn 2 plus, then I'm going to say plus 2 electrons to give me the final value of what? Of Zn there, right? So if I'm having that, then after that, I'm supposed to conclude 8.2.3, 8.2.3, which is the a balanced net reaction, right? So the net reaction of these two, I'm going to have that one is AL. So I'm going to say there, I'm going to balance everything there. So I'm going to have a 2AL. So it's going to be 2AL plus 2AL plus 3ZN, right? So 3ZN, then after that I'm going to say Zn 2 plus, right? Because we're having 2 there, right? So before maybe I can go there, let me just like show you why I'm using 2AL and all, right? So in terms of this, if we're to look at these two equations, right? So we need to balance the number of electrons, right? So for us to balance the number of electrons, you can see here at the top we're having 3 electrons, then at the bottom we're having 2, right? So it means the top part, the whole of this top part there, I'm supposed to multiply it by what? By a 2, right? Then the one at the bottom there, I'm going to multiply it by what? By 3, right? So the top part I multiply by 2 so that the number of electrons can be equal, right? So if you can look there at the top, so it means if I multiply by 2, I'm now going to have 2AL to give me 2AL, and then 3 plus, then plus how many electrons? Is going to be 6 electrons. The one at the bottom there is going to be 3Zn 2 plus, then plus how many electrons? 2 times 3 is going to be 6 electrons. Then I'm going to get a product of how many? 3Zn, like that, right? So in terms of this, now the net equation, we do not include the electrons, right? Because this one is going to cancel this one and then cancel that one out there, right? So now a balanced net equation is now going to look like this. I'm going to start with whatever I'm having on my left side is 2AL. Then what also do I have at the bottom is 3Zn 2 plus. Then I'm going to say now I've written everything that I'm having on my left hand side of the what? Of the arrow. Then I'm going to say arrow. Then on my right hand side, what do I have there? I'm having a 2AL, then 3 plus, then plus a 3Zn, right? So it's going to be 3Zn, like that. So this is how we attempt question 8.2.3, right? Then if we were to proceed to 8.3, so 8.3, we've been asked to identify a reducing agent, right? So remember, a reducing agent is the one that is oxidized, right? So the one that is oxidized there, it means what are we going to have? We're going to have our aluminum, which is a metal, right? So I'm going to say Al metal, right? So having said that, I hope you enjoyed the video. Thank you for watching.